started with lecture. Good morning, William. Get your clickers ready. We're going to do some wavelength and other calculations here to start class, so have your clickers ready. And we're actually going to do kind of a brain burner calculation here that hopefully will challenge you to think mentally about the things you're doing instead of just plugging in numbers. And while you guys are doing that, our two geniuses, GTA and LA, are over there trying out a few optics things for us to do as labs. Now, last time we were talking about optical rotation. And if you look up here, you'll see a set of gear up here. Look up here. Over here, not your phone. Over here. Everybody. Up here. Yeah. Good. Look. Okay. All right. So we're going to do optical rotation with this stuff. We're going to project it from the camera so everybody will see this white screen. And actually, you probably can, now that I look at it here, before you leave the classroom at the end of class, you'll probably be able to see this, almost everybody except maybe a few people you guys right down here. You'll just see the edge of it, but everybody else will see the laser dot on that white screen. But we'll have we got the camera aligned and everything looks good. So you'll be able to see that view. We talked about the amino acids and the sugars and the fact that they demonstrate optical rotation. They have this curious property of aminos being left-handed of natural origin and sugars are right-handed. And you were right. It is lysine. I looked up I made sure I have the image, and it was lysine. And the other one was glucose, as I figured. Here's you can't take a picture of this, or well, it'll be in the YouTube. You can't sketch this very well. This is L-lysine. This is from moleview.org. And one of them is L-lysine on the left, and the other one is D-lysine, which rotates dextro. It's right-handed. It's a synthetic form of lysine. L-lysine is the stuff that comes in nature most of the time. And can you see anything in that? Where they're the same chemical formula, same structure, except that they're not exactly the SAME. Anybody see that?
It looks like one of the bonds on the bottom is facing a different direction.
What color?
The one that's the blue bond.
Yeah, the nitrogen. Look at the other end. The nitrogens are slightly different. All right. So these are amino acids, and they build up proteins and stuff. So the blues, yeah, and they're not oriented exactly the same way. I don't know if they can be, but I tried to get them oriented, with the two reds, the two oxygens. Oxygen is red, right? That's oxygen. I try to get those to the lower right and stuff. And so, anyways, you can see that they're not mirror images of each other. They have the same. They're isomers, but they're not mirror images of each other. So it's a significant thing. And biologists, they don't know the reason. Nobody knows the reason for that. All right, let's do some calculations. So click your clicker on. We're going to do numeric answers. So you'll be hitting the send key. And what we're going to do is calculate some frequencies and wavelengths in the, some frequencies in the Balmer series. Now, the Balmer series is the visible set of discrete colors of hydrogen that we saw on the first day of class. Okay, and this is the hydrogen lamp, or this is like the hydrogen lamp that we had up here in the front. And then when we looked at it through the diffraction grating, it looks something like this. And the central image is over here on the left. And then over here, there's your first bunch of diffraction lines. Now this image was taken by me with a camera in the lecture hall, actually in 260 in the basement here for a big lecture section, and we were just doing the same thing. But except um, we had a big diffraction grating about the size of this thing. All right, so I took my cell phone and I shot it. I got a good diffraction set of diffraction lines, and I tried to get a photo of it plus the central image. So it's a little bit shaky, but that is a genuine. Uh, and that one out there, that aqua colored line, is called the H beta, the hydrogen beta line. And then the other ones are hydrogen gamma and delta. That's actually two lines, those purpley. And actually, there's three of them there. And I'll show you that in a second here. This is actually, let me turn the lights off. Let me see here. 25%. All lights off. Okay, so on this one, you can see the beautiful red H alpha line to the far right. And I've got H beta. That's the next one. That's kind of aqua. We're going to calculate the frequency for that. And then you can actually see two fairly bright purpley blue lines to the left of that. And actually, there's a faint, uh, uh, really deep in the purples line out there to the left. Now, this is the view from a good quality spectrometer. In other words, not like that shaky one that I took in the lecture hall, where I'm kind of holding my cell phone in a big, low quality. This is a high quality diffraction grating, high quality optics. And from this, you can make high quality angle measurements and easily figure out the wavelength. Now, let me go back up to regular lighting here. Here's your first question. The wavelength of the aqua H beta line is 486 nanometers. We get it with trig and a good spectrometer. Calculate the frequency in terahertz. Now remember, a terahertz is 10 to the 12th seconds to the minus 1. All right, so go ahead and calculate that. And let me start your question here. Terahertz, tera is 10 to the 12th. Yeah, and then nanometers is 10 to the minus 9 meters. So. No, I just want to, but maybe for Wednesday. Do you get any ideas? Is there like a sheet of things to do in there, like there? Did you get anything? I forgot about the magnet probe, just fooling it around. Right, so I want to be able to, all right, okay. Can you guys take some time to write up a procedure that the students could do? do it right now. Just and you're dismissed from other things if you can get that done for me. Make that your so get your brain waves together and see if you can just something simple. You know, a couple three. Uh, could you bring me some of that papyrus from over there? Two or three. You know, enough, more than definitely more than one, and just figure out what's good. What can they do? What's cool? No, nothing too complicated. Type in your answer, hit the send key.
But you just want like the
17, 23, 60, 65, 70, 2, 6, 77. 1 minute.
This
15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, the answer is 617. Now, let's take a look at the answer set here. There's a little bit of disasterness. A lot of you have got 617. Good. Now, if you had 6173, whoops, you mishandled your scientific notation a little bit. You got the right numbers, the right numbers in there, but you didn't have the right power of 10. Same thing here, 6172. Same thing here, 0.617, and same thing down here. Now, if this were a test, I would maybe give these guys partial credit. Not a lot, but I mean, you got to know how you do your scientific notation here. I mean, there's no substitute for it. What? Yeah, but that's because of that's not four significant figures. That's well, okay, that is four significant, but you don't have to actually count the 0 for significant figures.
that's why I thought you would put it in because you don't have to.
Yeah, so this one I just went to the nearest to the nearest terahertz. So and I'm not going to give you a what if that's close to the real answer. So I have to figure out something that's either way bigger or way smaller than 617 terahertz. All right, now next question is hold on a second. Next question is alphanumeric. Now this one's multiple choice, but it's more than one, and or excuse me, it's more than 5. All right, so it's a long list of multiple choice. And so let me switch over to alphanumeric. Now, this problem, it's going to take you some time because what I want you to do is calculate the wavelength first for a 563.9 terahertz laser. All right, and then give the color estimate. So the first thing I want you to do is get that wavelength and then figure, all right, this is going to be, A, B, C, D, E, F, or G. Right, and these are all. This is just Roy G. Biv, so it's so take your time, calculate a wavelength, and then figure out the color. Then we'll get the wavelength on the next question. That'll be the numeric answer part of the answer. And this is a valid thing to be able to do. Get a wavelength, Michaela, somewhere, some number of nanometers, and they say, oh, that's going to be a green or something like that, or that's going to be a red, or somewhere in the Roy G. Bibbs. And this little guide down there will give you the scoop on that. 273 nanometers, 563.9 terahertz. Yeah, so this one you're going to need to handle your scientific notation carefully again, at this level. Where's Melanie Del Toro? Paul Zumay, did you get the homework done? Good. I saw a few people didn't, so. Any guesses as to what kind of calculations you're going to find on exam 3? Wild and crazy guess? What could it be? Yeah. I want a letter A, B, C, D, E, F, or G. I just want the color. The next question, I'm going to give you I want the numeric answer. So keep that in reserve, and I'll get that on the next question. Meanwhile, I'm using Instagram here in class. Sweet.
Yeah.
All right. 30 seconds to answer. Starting right now. Make sure to hit the send key. Take a look at your answers. Oh my goodness. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Close question. Yeah, it looks like you guys are geniuses today. Everybody got that right. So that means you've got your wavelength. Let's get that now. Okay, go back to numeric, hit the refresh key. Is this going to be numeric? So this is your numeric answer. This is the number of wavelengths. Okay, nearest nanometer, please. And watch your scientific notation. Because I'm not going to ask you to put any more of those EE minus fives or anything like that in there. You know, I'm just going to say give me nanometers. We call it good. What? Yeah, usually I have, I don't know if I had that on the cover page, but usually when once we start doing nanometers and stuff like this, I put that on the cover. You know, like 1.00 nanometers equals 1.00 times 10 to the minus 9 meters. Yeah, because I always have to look that stuff up. So if I have to look it up, you know, I put it on the cover. Okay, 30 seconds starting right now. So I want a whole number and then hit the send key. Christopher, did you get a good answer? Are you in the 400 to 700? Are you in the 400 to 7? It is a big range. Are you somewhere in there? Yeah, okay. He's not? Really? 2 nanometers? Well, now you're messing with me. I was asking an honest question. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see what you guys have got. Oh my goodness. Well, we do have a little bit of explaining to do here. Again, yeah, the correct answer is 532. And again, we got some powers of 10 problems here. And those are the frequency. Yeah, this is no good. This should be that's the frequency, and it's not even right. So for those of you that have 5.32, remember visible light. You know, it doesn't say visible light, but a few hundred, when you've got hundreds of terahertz, you know, 200, 300, 400, 500 terahertz, think visible light. All right. And visible light is 400, somewhere between 400 and 700 nanometers. So if you come up with 5.32, you should say to yourself, "Uh-oh, did I forget a power of 10? Did I take out too many powers of 10?" All right, and that's what it looks like on this. So anyways, just a word to the wise on that. Now let me back this out of here. And what I want to do now is, we've done a little bit of reinforcement for the homework, and I hope that most of you have done the homework. I noticed that there were some people that didn't do it as of about 8 this morning when I looked, but about 80 of you had, so that's pretty good. I want to do some sketches to reinforce this idea of polarized light, because as you can see over there in the corner, Kendra and Andrew are working with an optics kit that you guys are going to use. All these little blue boxes up here, every team is going to have one of these. I think Wednesday maybe, and we're going to do some optics, some stuff maybe a little bit like what we're going to do today. Although you're not going to have K-roll. Where's the K-roll corn syrup, by the way? Is that up here? Oh, okay. Oh yeah. Okay. So this demonstration up here, I'm going to do some sketches and stuff before we get to it. All right. So let's go to the document cam and bend my. All right, and let's do a little bit of sketching. Over here. Let's try to do this without. All right. All right, now let me. All right. Let me draw a picture of an H2O molecule. All right. And in fact, let me put a little sailboat in here too for reference. Yay. Okay. And what we're going to do is use that to, and I'm going to put my pencil in here too. Now this is a polarizer. Okay, and let me hold this up. Take a look. This big thing that I'm holding up. You looking? Harun Rashid, come on. You look at this. This is a polarizer. All right. And unfortunately, it's got all kinds of fingerprints on it. Oh my goodness. This thing is filthy. But anyways, now this is like your sunglasses. Now, so you've got a pair of sunglasses that you look through, and it's especially good if you're out on the water, because the water, light reflected off the surface of the water, especially still water, is polarized, and it can cause a lot of glare. So you can cut a lot of glare down with lenses like this. Now this is nice, and you can see, I'll just put this down. Actually, let me just put this down. Let's see if this will pick up the. You can kind of see the oxygen molecule, but the sailboat is a little bit. Let me get. Brad, can you give me my pencil case there? All right, let's see if I could draw something in blue. I don't have any blue pen. Anybody have a blue pen or any kind of a marker? Destiny, have you got something? Thanks. All right. Let's draw a shark. Okay, there's a scary shark. Let's see if that'll be. Oh, look at that. Very nice. All right, so you can see the scary shark. Now, what you guys can't see here is that around the edge of this is a bunch of degree numbers. Like here's 315 right here where my index finger is. And then this is 330. And this is 345. And this is 0. In other words, 360. And they mark every 15 degrees around the circle. Now you can't really see. I guess maybe up here you can kind of see something. What can you see up there? What is that number up there? You know, I have a hard time seeing it myself. Let me put on my specs. If you don't have the light just right, oh, let me try to do it like this. All right, see those numbers? All right. So you've got those all the way around. Now, the reason for that is, you know, one polarizing sheet, you don't really notice anything. It's when you have two of them stacked on top of each other, that's when you start to notice something. Now, I'm going to put this other one on top. Now, it's, hey, wait. Does this thing, it doesn't light up. Yeah, Brad, can you help me with this? There's a symbol over there for lights, light bulbs, the light bulb on the side. See that? Okay, off. All right. Now look at that. You can't see Jack. Now what I'm going to do, whoa, I'm just twisting this a little bit. Now let me twist it back. Let's see if we can recover the image. There it is. All right. So what this is doing, I'm crossing two polarizers. When the polarizers are 90 degrees apart, and you'll be doing this in the lab, you know, probably Wednesday. When they're 90 degrees apart, then light of the light polarized by this polarizer cannot get through the second polarizer. All right. So now let's look at these numbers. Yeah, this is 0, 0. Right here is no. All right, look at this. This is 60 on the top one, and over here is 265. All right, so that's about 300 to 200 degrees difference. Let's see if we can rotate. All right, now it's going black again. Let's try to keep rotating it counterclockwise here and see if we can recover. This works really good on an overhead projector, but I don't think we have. Is there one? Hey, Andrew, can you go see if Ray has an overhead projector on wheels? Take time out from that. Let's see if we can recover the image. We'll have to go 90 degrees. There we go. All right, we got it again. All right, so there's my sailboat. All right, and now this number up here, oh, look at that. This number up here is 255, and so is this one up here. So now the polarizers are aligned here. All right, the polarizers are aligned. If I go 180 degrees around, back over to 75, all right, let's see, this is 75 right here. I've got the images. So when I go 180 degrees from having the image, this is parallel polarizations. If I go 90 degrees, so from 75 down to 345, bang, I get zip zap. All right. Now I want to do some sketching with this. Brad, can you turn those lights back on? All right, so we're going to do some sketching now. And, you know, on the internet, just look up crossed polarizers, and you'll see buku examples of this. So polarizers and crossed polarizers. And if you do that, you'll see a lot of YouTubes. I haven't even looked, and I know that they've got them. And you'll get a bunch of physics nerds showing you, you know, everything I did, except it'll be much nicer. All right. Now, here's the idea of what's going on with the cross polarizers. Go ahead and draw a side view, kind of a perspective view. Here's your optic axis. Okay, so this is like the z-axis here. All right. And then here's the y-axis. And then here's the x-axis. Actually, this is the y-axis here. This would be the z-axis up here. Okay, so now what I want to do is draw in a pair of lines. Huh? Okay. It's all right. Go ahead and continue with what you were doing. All right, so that represents the polarization. You know, Destiny, this is really nice, this marker. Okay, so this is like 0 degrees and 180 degrees, you know, on these big jobs with the angle markings. All right. Now we're going to say that the light is propagating towards the y-axis. Okay, so this is the positive. I'll write y subscript positive, x subscript positive, and then this is z subscript or superscript positive. Okay, so those are the positive x, y, and z axes. So the polarization axis is parallel to the z-axis. Okay, and basically what it is a bunch of molecules arranged in a certain way that permit light to go through if the electric field of the light is oscillating. Like, so there's the electric field, and I'll make it red. So there's a sine curve for the E field amplitude, I should say. Okay, and also it's moving. I'll put an arrow to signify the speed of light this way. So it's moving at the speed of light in that direction towards positive y-axis. Okay, so what that means is that E of t and x is equal to E0 times k hat, and k hat is the unit vector along the z-axis times the sine of kx minus omega t for whatever color. Now this is white light, so this is all different. You know, this projector stuff we're projecting, but we're going to use. Oh, by the way, the green laser that we are going to use for this optics demonstration is 532 nanometers. So that's why we did that little calculation. So that's all in here. Here's the wave number that we talked about last time, the angular frequency, right? So this is the sine wave, okay, that describes it over space-time, and it's parallel to the z-axis. So k hat is the unit vector in that direction. I is the unit vector in the x direction, and j hat is the one that symbolizes the unit vector in the y direction. Okay, so this lets all the e's, now they're oscillating, from positive to negative to positive again. So here's E0, there's the magnitude E0 up here, and here's minus E0 down there, and here's E0 up here, this magnitude, here's minus E0 down here, etc., etc. All right, now that's what the polarizer does. Now this is not sketching in the magnetic field, but and I'm not that good of a sketch artist, but there's diagrams in the textbook that we have already looked at that have the magnetic field kind of perpendicular. So the magnetic field B is going to look like, actually this should be E of t and y, and this should be ky here, and this because it's going along the y-axis. So this would be B0 times times, now it's going to be perpendicular to that. So this would be B0 times I hat. Wait a minute, E cross B. Yeah. So that's going to be like this. And this is going to be like a sine of ky minus omega t. And remember, k here is 2 pi over lambda. So don't confuse it with the k hat vector up here. Okay. So B is perpendicular. Whatever E is, B is perpendicular. And so remember, E and B are always perpendicular. And they travel at the speed of light. They oscillate at a certain frequency and so on and so forth. Okay, now that's, so this sketch is kind of sketching what the polarizer does for the electric field. The magnetic field is in there too, but we're not going to sketch it. But you can see different sketches in the textbook for that. Now I'm going to go to another page, and let me go to the next, back to this. You're copying this down. It's going to be embedded in the YouTube, as always. Gosh. As Napoleon Dynamite would say. What do you think? Gosh. All right. So now let me draw another. I'll draw down here since you guys are kind of slow on the sketching. Now here's what my polarizer look. Go ahead and draw a face-in view, and I'll draw some. Here's my polarization axis. I don't know any better way to write it than that. All right. Now let's draw a propagation axis right in the center, and that's going to be a little circle with an X to symbolize that that's the direction that the light is going. And it's the same one here. All right, the same. But now, who was that? Was that you? Oh, at all. All right, let's look at an alternate beam that's tilted at theta, some angle theta. So now instead of the polarization axis here is still parallel to the z-axis. So go ahead and draw in the z-axis here if you want. I'll just kind of gently sketch it in here. Okay, so there's your z-axis. And we'll go ahead and sketch the x-axis here. And the y-axis is the one into the page. All right, now let's do an electric field vector. And now I'm going to have a different polarization. It's not going to be vertically polarized. It's going to be polarized like this. Now the way to represent this is a double arrow to represent the bottom and the, the oscillation from top of the wave to the trough of the wave, from top of the wave back to trough of the wave. So you do that with a double arrow here. Okay. Now let's put a tilt angle in here. Theta. Okay, so let's say that we tilt it theta degrees away from the polarization axis. All right, now that's going to be important for us because, all right, now I'm going to go to the next one. And I'll just redo the sketch maybe a little bit bigger and nicer here. Okay, there's the polarizer. Here's the z-axis. Here's the x-axis. And right here in the middle, a circle with an x in it. There's the propagation axis. So this is the polarization up here, and here's the x-axis. And now I'm going to try to draw my arrow a little bit bigger. So I'll just say it's tilted at some angle theta here. And I'll make it a little bit bigger. Okay, so here's my range in. All right. So now my I can't use it's not parallel to the z-axis. All right, so you cannot use k hat by itself. You have to use a little bit of I hat. For if you want to do this, now we're not going to dwell on that, but what we do want to think about is that it's tilted. Now, does this beam have a component that does scamper through the polarization axis? And the answer to that is yes, it does. So what amount of E, of this E, this alternate E, passes the polarizer? So the answer to that is basically this. Here's my E. So here's E at its maximum. Okay. Here's theta. Here's the polarization axis here. And the component parallel to the optic axis, or to the polarization axis, is E cosine theta. So whatever the magnitude of the hypotenuse is, the stuff that scampers through there is in this amount. Now the stuff up here, E sine theta, gets absorbed by the molecules that make the polarizer a polarizer. So basically what you're doing is you're warming up your polarizer with that component. You're exciting the molecules. You're making them rattle a little bit more than they would otherwise. And so they're getting a little bit hotter, not by a whole lot, but because otherwise your polarized sunglasses would start on fire. Now who's that guy? Which is the X-Men? Cyclops. So think about the polarizers he has to wear. Oh my goodness. All right. So the polarizer absorbs this component up here, but it passes. The polarizer passes E cosine theta. All right. So you're getting a little bit of newtons per coulomb to propagate through there, and also with that, you're getting some magnetic field. Now we're just concentrating on the electric field here. All right. Now, what I want to point out to you is this, that the intensity is proportional to the square of the electric field. All right. So the intensity after polarization passing is equal to E squared times the cosine squared, or E0 squared, times the cosine squared of theta. And this is called the law of Malice, after the guy that figured it out. No, not the law of hatred, the law of malice, M-A-L-I-C-E, but the law of Malice, the man, M-A-L-U-S. And so what it says is that basically your intensity goes to whatever your original intensity is times cosine squared of theta. Okay, and actually this is Malice's law. Okay, this is Malice's law in terms of an electric field. So let's make this I as a function of theta. Okay, and the theta has to be oriented in this way from the polarization axis. So you got to, now what does that mean? Well, cosine squared of theta goes through, let's see, its maximum when the cosine of theta is equal to 1 or minus 1. And let's see, the cosine of theta is 1 at theta equals 0 or theta equals 180 degrees. And that's what we found. When the polarizer, the second polarizer was aligned, second polarizer aligned with first. Okay, so your first one sends it through at an angle, say, and then if your second one lines up with that, then you get maximum throughput, maximum intensity. Additionally, it's a minimum when cosine theta is equal to 0. So that means theta equals, let's see, the cosine of theta is equal to 0 at pi over 2 or 3 pi over 2. Or as we say in the business, 90 degrees or 270 degrees, right? So now this effect here, 90 degrees, that's your cutoff angle. If you have a polarized incoming light and you totally extinguish it, that means that your polarization axis is exactly orthogonal, perpendicular to your to the incoming light's axis. So if your light's coming in like this, like at this angle theta up here, you're going to get transmission until you rotate your polarizer over to theta. All right. And that's how we saw the signal disappear. All right. Matter of fact, when you guys are, hey, Andrew and Kendra, are they going to be able to show the law of Malice on that thing? Are you getting angular extinction? Yeah, in other words, cosine squared of theta. Are you getting extinction with angle? 90 degrees and so okay, good. All right, so you guys are going to be doing that in the polarization lab. All right. Now, a couple things I want to show you. Let's go to the next slide. In general, so this is kind of comments in general. The way that you represent an unpolarized beam of light is by a bunch of arrows like this, tilted in several different directions. And then here's your polarizer up here, and then here's maybe another polarizer up here. And here's your optic axis. Here's your, okay. And so when you have something like that, this signifies unpolarized. And in general, most incandescent lights will not have polarized light until you send it through. Now, if this is your optic axis here, all right, then the output is, and let's say that the propagation direction is like this. So speed of light going in this direction. So your output now is vertically polarized, parallel to the axis. Okay. And so if your second one is also vertically aligned, so here's your other optic axis, then it'll just pass through. All right, so there's your output, your throughput. Now, let me do a case of extinction. All right, so here's unpolarized light. Just kind of chaotically aligned, and it's just, so you get some of it, all the different tilt angles randomly every second. All right, so here's your first polarizer. All right, so let's say that the polarizer's axis is like this. Okay, and so the output is a vertically polarized beam. All right, now let's make the second polarizer over here. Let's give its optic axis a little bit of a tilt. And for comparison, I'm going to draw in a dotted line of the previous. Okay. Now what that means is that the stuff coming out is going to be parallel to this new axis. So the new axis, and I'll put angle theta up here, relative to original, or to the first axis. Okay, this is the first axis. And so this stuff's going to come out at a slant, parallel to the, and it's going to be smaller, so it's going to be less. The intensity is going to be cosine squared of theta. So try to make this arrow a little bit smaller over here. And just for comparison, you can trace in theta here if you want. Okay. And there's diagrams in the book. Now, remember, if you want to see diagrams, nicely drawn diagrams instead of my kind of, just type in Malice's law and you'll see buku diagrams of that. So unpolarized gets polarized, then gets semi-extinguished here. Now the other this is 100% transmission. And this one is the intensity is equal to I0 times cosine squared of theta. And let's say that this is I0 over here. So the incoming, no, let's not say that. Let's say that this is I0. Okay. So the incoming intensity into the second polarizer gets zapped by a factor of cosine squared of theta. And then, of course, the third one is incoming unpolarized into a vertically polarizing I0 vertically polarized. And then if your second polarizer now is polarized perpendicular to that, so that this angle here is 90, okay, 90 degrees, you get zip zap over here. Okay, you've extinguished it, because when the axes are 90 degrees apart, cosine squared is zip zap. So you don't get any, so you've extinguished. Okay, so here's unpolarized. Here's vertically polarized. And then over here is zip zap. And then this one up here is partially polarized or repolarized. Now what we're going to be doing, this is what polarizers do. What I'm going to be showing you up here, are you guys almost? Where did they go? They were kidnapped by aliens. Well, what we're going to do in a minute, as soon as they get back to help with this demonstration, is I'm going to show you how this corn syrup up here does the same thing as this. Hey, are you guys done yet? What are you getting, snacks? You're, oh, cool, light meters. Could you come up here and help with the cameras now for a few minutes? All right, now what we're going to do, and let me go to the next slide here. Go ahead and turn on the cam. Also, turn the lights down to 50%. All right. Now, remember, what we're doing here is we're aiming. Can you take that laser off the track with this? With it? No, don't unscrew it. Can you lift it off the track? It's bolted. Okay. So what we have up here is a laser pointer. Okay, and Kendra, point to the laser. Can you swing it around to see the? No, not the blue boxes. What do you think this is? A Kmart special? Blue light shoppers. Okay, so there's the laser pointer. All right, now put your finger on the first polarizer. Okay, so that's there. Now, from this angle, you can't see that it can be turned, but when we realign it, hopefully, you'll be able to see that it can be turned, okay? Now, okay, Andrew, swing it around so we can see everything. Andrew's kind of new at this, and he's doing better than me, so I shouldn't say anything. All right, now, put your hand on the second. Now, here's the second polarizer. You guys up here close can see it, okay, but everybody else can look at it. So that's the one that we're going to use to extinguish the unpolarized light coming out of the laser, out of the pointer. All right. All right. This is almost perfect. Can you move the first polarizer a little bit closer to the carriage, to the scissors? A little bit. I want you to be able to put your hand, good, between right there and also on the other side of it. So move the scissors over a little bit. Can you do that? Don't worry, don't mess with it. That should be enough. All right, now, can you get back to the pointer? All right. Go ahead and turn on the laser pointer. Okay. Go ahead and put your hand in front of it. All right. Now, can you see it on her hand? All right. Now, other side of the polarizer. All right. So it's going through there. All right. So her hand right now has got vertically polarized. Actually, can you back it? You can't really see, but the polarization axis is marked by a yellow tab at the top. Okay, now you can see it on the other one in perspective. Right? You can see it on that one, and they're aligned. Okay, so go ahead. So the stuff hitting Kendra's hand right now is vertically polarized. Basically, in this direction. All right, take your hand off. All right, now you can see it. Now put it over there in front of the second polarizer. All right, so there's the incoming to the second polarizer, and you can see that the vertical polarizer is polarized vertically. Now we can swing that around just like I did these big ones. All right, now go to the other side. All right, so she's got some throughput. So that's on the downhill side of the second polarizer. All right. And so go ahead, let's get a long shot now and get the white screen. Now we're not going to mess with the first polarizer. Okay. All right, take your hand away. All right, so there's what it looks like coming through. Now everybody can see that. And you people up in front can see it. The only people, Christine, I don't know if you can see it from where you are, but you can see it on the screen. Okay. Now, let's see if we can rotate the second polarizer 90 degrees. So that yellow tab, bring it 90 degrees. Let's see if we can extinguish. Dun, 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 dun. There it is. 90 degrees. All right, now bring it around and do 90 degrees in my direction. All right, so here we go. We're up at the top. All right, max intensity on the output. Now we're, all right. All right, so this is Malice's law visually. All right, so it's not a lie. And if we put over here at the white screen, if we put do you guys have photo detectors over there?
Yeah, we haven't figured out how to use them.
Okay. All right, so go ahead and show that on the screen. So what Kendra's got here is a photo detector, and the very top of it, turn the top towards the camera. Okay, that is a photo cell. All right, and we're going to use that as soon as Kendra and Andrew can figure out what to do with it. Ooh, you know what? I wonder. You owe hours.
Okay.
Kendra doesn't. She's a learning assistant. I'm going to deputize you to take one of these things home and really, crush it.
I found a lab manual.
You did?
Yeah, I found it. I emailed it to you on web courses.
Great. All right. So she's fooling around with the light meter. But anyways, we'll be hopefully able to do the light meters on Wednesday with the kit. Now, That's all the stuff I was sketching before. Now we're going to do something with the K-row syrup. Now you may be saying to yourself, Dr. B, what is this business that you keep talking about with K-row syrup? So let me hobble around over here, and now I'll take over the whole point. This, my wonderful students, is K-row syrup. You got to be really careful with it because it's really sticky. Apparently, it's sweet. And if you drank like a thimbleful of this, you'd go into diabetic shock from the amount of sugar. So this is high fructose corn syrup, the worst thing that you can eat, just about. All right, but it's filled with glucose or sucrose, I suppose, or fructose, high fructose. It's filled with an optically active molecule. Now, Kendra, you're not dismissed. She's got the light meter. All right, now Kendra's going to rip the label off this K-row syrup. All right, so she's ripped from existence the label of the K-row. So the only reason for that label was so that you guys could see what it is. Because what we want to do is, oh man, there's all kinds of glue here. This sucks. Do you have any hand wipes? Has anybody got a hand wipe? Or like from can I borrow that? Yeah, from Chick-fil-A. Here, I'll open it. Because this stuff will take off just about anything. So, did you need this for your lunch?
A couple times ago, Chick-fil-A's really good.
She's gonna eat wings for lunch today.
You need two of these. When you go to Chick-fil-A, you need two. One for before and one for after, because you figured it out. And this thing is still caked. All right, we'll save this for later. But instead, what I have up here is look at this thing. This is so thick. Can you see? Look how thick this stuff is. You can't really see, but it's like totally thick. This is a small beaker filled with K-row syrup. All right, now if you don't believe me, you can come up and stick a finger in it after class and taste it and get immediately sick by how sweet it is. All right, let's turn off the laser pointer. Okay, let's get the two polarizers perfectly aligned so that we have 100% transmission. So parallels. All right. So what we've got is parallels. We haven't done anything with the first one over here, but we've changed the second one. Okay, turn the light on. All right, so there's our max. Now Maya, stop beating up that boy. Please try to pay attention. Okay, this is serious now, because we're going to demonstrate optical rotation. Now this thing is it's vertically polarized here, right here where my hand is. Same polarization here because the two polarizers are aligned, at 0 degrees. Now let's put this in here. Oh, okay, Kendra, you want to align that?
Yeah.
And you can see that we've got a problem. Take it off. Max, go ahead and put it back on. And the problem is that it has to be going through perpendicular. All right, we're getting a little reflection.
I mean, this is what we're supposed to be getting since they're
Yeah,
away.
so now this is not perfectly extinguished because we're not using the best kind of a container here. This is curved, and what we should do is have something that's shaped a lot like a polarizer with surfaces like this, fore and aft, instead of surfaces like this, fore and aft. All right, let's rotate the second pole. Now, get your hand out of the way. All right. So use your hand up here, and let's get max. Let's get back to max. There we go. And look at that. This second polarizer is at 90%. So the stuff coming out over here is polarized like this by the corn syrup. It's rotated at about 90%, 90 degrees. Now, the optically active, optical rotation. We've rotated with the corn syrup molecules. And the more that you have, I mean, you can make it go a full turn on 360 if you have a long cylinder of corn syrup. In fact, that's how you can tell a lot of these properties. Now, here's a little tiny cylinder. Can you align that one? And this one's kind of messed up because we're getting it's right at the surface of the.
It depends because these are.
See, we're getting diffraction there. See, this thing's got lines on it. There. Okay. Let's see if we can analyze. We can extinguish this. Whoa! Look at that. Keep going. All right. We're getting. Well, go back up. All right. Oh, there it is. That's pretty much extinguished. Now notice where the angle is. What's the angle there? Looks like it's about 45 degrees for this little teeny rectangular cell. Now you guys are going to measure some of this stuff on Wednesday, hopefully. All right. So what this shows you is if you have a very small thickness of corn syrup that you're going through, it rotates, but not as much as the big beaker full. All right. All right. That's optical rotation, my wonderful students. That's a nice diagram. All right. Now, you can you take that? Do they have a sink down in Ray's office? Don't spill that. It's really sticky. It makes a mess. Kendra's over here trying to give me a heart attack. All right. Now, go to the 100% light and laptop. Okay, Kendra, you can take the. You guys can both go back. I'll operate from here. Okay, so that's optical rotation. And so if you want to look it up in Google, just type in optical rotation or Karo syrup, and then optical rotation. Karo syrup is frequently used, so that's why you can see it all the time. All right, now I want to talk about Doppler shift. Get your clickers ready. We're going to do a calculation. And this is something that we've talked about in Physics 2053. One of the ones in 2053 that we talked about was sound wave Doppler shifting. And that's the stuff that, at least in my lecture, we listened to a freight train on YouTube, and it, the train, as it passes by the guy with the camera, it goes from a high pitch, the horn goes from a higher pitch to a lower pitch as it passes the guy. So approaching, it has a high pitch. Receding from the observer has a lower pitch. Now that's it for freight trains. Ultrasound in medical devices is pretty important too. So this is, from a neonatologist website. They're looking at the umbilical cord, the artery, and they try to look at different structures and stuff in the umbilical cord. So ultrasound devices use that a lot. You also see it with radar. Here's, you can judge the speed of cells in the bloodstream with ultrasound. It's kind of cool. Now, electromagnetic Doppler shifting, we use that for radar. I mean, you go to WFTV Channel 9 Eyewitness News website, they got a Doppler radar. You can always look up the, whatever the storms are doing, or not. Sometimes you don't see jack, which is nice. But anyway, so weather radar, speed guns use Doppler shift. So if you've ever been, well, I'll just say it this way. I know all of you are nice young men and nice young ladies. You've never violated the speed laws. But I humbly admit that, yes, I have done so a few times inadvertently. And other people get nabbed. So there's a cop trying to nab somebody. But see, I use cruise control in my vehicle now. My new vehicle, I have cruise control. So I hardly, no tickets for Dr. B. But now, I'm going to show you how Doppler shift works for these babies. But we also use it in a lot of other applications in physics. Now, this is one that is extremely important for those of us that study the early universe, the age of the universe, the expanding universe, as the saying goes. You measure, what we found is that the further a galaxy is away from us, the bigger the redshift in, for instance, its H alpha line. Its H alpha line is, some of them are actually shifted down into the infrared. They're shifted down into the reds, and nearby galaxies, it's just a little bit of a change in the wavelength. So H alpha is 656. So a redshift would be 657, 658, and longer. And we've actually seen stuff redshifted into the infrared. And what that does is it tells us that all the galaxies of the universe are receding from us, the expanding universe. That was the tip-off. Now, all Doppler effects, whether it's sound wave or electromagnetic waves, depends on the relative motion between the source and the observer. All right. Now, for the astronomer, the source is the galaxy. The H alpha in that galaxy, all the hydrogen in that galaxy gets excited and sends out some photons of light, and by the time it gets to Earth, it's been redshifted. For the freight train, the source is the train. The observer is the guy with the camera, if he's got his audio, microphone on. Oh my goodness, it's almost time to depart. We got 10 minutes. That's all right, we'll do a little bit of this. If the source is moving relative to the observer, then you're going to see you're going to be able to see a Doppler shift, either a blue shift if it's coming towards you, or a red shift if it's moving away from you. Now the cops use this. What they do is they bounce a 2 gig signal off your car. And then they listen to the bounce back, the echo off your car. So your car is the source, and the observer is the police officer. And if it doesn't come in at exactly 2.00000 gigs, he can tell you're moving. And if it comes in with a little bit too much of a Doppler shift, either higher frequency or lower frequency, you're busted. Okay? Which, has happened to me. Now this is what we call, this is a weather radar. This is a phased array radar up here. Right? It's a panel of, radar emitters and absorbers over here. You can see a couple guys there with a step ladder. So that's a fairly big, it's 4 or 5 meters across. And you see them on naval warships. Now this one here, this is a Doppler, this is a radar, phased array radar. They track things from space with those babies. And you can see they've got domes up on top as well. Now those are covered up. But that one in front is a phased array radar. And that's so they can shoot down, hopefully, if the North Koreans or anybody else ever decides to take a pot shot at the United States, these guys on the Chancellorsville CG-62 will knock it out of the sky using that phased array radar. Hopefully. At least that's what they're training for. Now here's the formula for the redshift. The symbol we customarily use for it is Z, delta lambda over lambda. And that's the change in the wavelength. So if something's coming back to you with a smaller frequency, that means it has a bigger wavelength. All right. So if the train is moving away from you, you hear it at a slightly deeper note. That means a lower frequency, bigger wavelength. So that means you've got a delta lambda up on top. Now lambda is the outgoing frequency. So for a train, if you were in the train station and the train was stopped and you got the guy to blow the horn, that would be the normal pitch at rest. When he's moving away from you, the pitch will sound just a little bit less than that. When he's moving towards you, it'll sound a little bit higher than that. So you guys doing good here or what? Okay, good. You're deputized to take this home and fool around with it or up in your office or something, but you got to bring it. Yeah. What's that? Yeah, I think you are. I'm deputizing you. This is like the 60s technology. All right, so try to find out what you can with this. All right, so you get a wavelength shift, and you can do a frequency shift as well. Now, that factor Z is equal to now this is from relativity. This is for electromagnetic radiation here. It's a relativity formula. It's pretty fancy, but you guys could handle it if you wanted to. 1 plus V over C in the numerator, 1 minus V over C, V of the speed of the source, and then square root the whole quotient, and that's going to be your Z, your redshift, delta lambda over lambda. So if you're a cop, you know what lambda is. They build a certain frequency and wavelength for your speed gun, all right? And then you measure the incoming frequency and wavelength, and then you check for delta. Now in a terrestrial application where you have very, very small speeds, that big square root basically boils down to this. This is close enough for government work, so go ahead and write this one down. Frequency observed, so that's your bounce back. All right? And the frequency of the source, that's the radar gun. All right? So the echo is F subscript O. Now, the relative speed between the observer and the source is the numerator of that stuff inside. Now, there's no square root there. It's an approximation when you have very, very small velocities. Now, terrestrially speaking, that's perfectly fine for us. And if you work it out, this is the formula that is programmed into those speed guns. All right? The beat frequency is the numerator. That's delta F, the difference between the outgoing and the incoming frequencies. And then the F subscript S in the denominator, that's the factory setting for the oscillator. So 2 gigs or whatever it happens to be. And that's just simply equal to that ratio is equal to minus or plus the car speed divided by the speed of light. Now, you've got to be able to get a beat frequency in the order of a few hundred hertz to get a speed from a 2 gig, 3 gig radar gun. So radar is up there in a few gigahertz, right? To do that, so your frequency down the denominator has got to be a few gigahertz. So that delta F up there has got to be, at the level of a few hundred hertz. Now audibly, if you turn that into an audio signal, that'd be something that we could hear, like a middle C or any other musical notes. If you have something like that, a frequency at that level, you can figure out the speed pretty good. All right. Now we're going to dismiss, but I'm going to show you the first problem that we'll have on Wednesday, and it's this one right here. A police officer measures a beat frequency of 266 hertz using a 2 gig radar gun. Calculate the speed of the car to the nearest meters per second. And we'll do that on Wednesday. Go ahead and you're dismissed.